So we're going to start with number 7, where it's asking how fast must a ping pong ball move in order to have the same kinetic energy as its baseball. And the key understanding here is that you want to make sure that you have in your Y, in number 7 here, is that kinetic energy is energy of motion. And you might also show that you understand that relationship in that the ping pong ball will have to move faster than the baseball, since it has a lower inertia. So the ping pong ball has a much lower inertia, and that's going to relate to the fact that it's going to have to move faster to have the same amount of energy, since kinetic energy is about energy of motion. Alright? So, using that idea right over in my how, I'd start off with my definition of kinetic energy, 1/2 the inertia times the speed squared. Problem says that the kinetic energy of the ping pong ball has to be the same as the kinetic energy of the baseball. 1/2 inertia of the ping pong ball, velocity of the speed of the ping pong ball equals 1/2 the inertia of the baseball, speed of the baseball. Anything cancel out? Sure, my 1/2s, right? They're on both sides. Now I can start substituting in the inertia of my ping pong ball. 2.7 grams. What's my base unit of inertia though? Kilograms. So I need to put in 0.0027 kilograms. I don't know the speed of my ping pong ball. That's what I'm looking for. The inertia of my baseball, 145 grams. So in kilograms, that's 0.145 kilograms. And the speed of my baseball is 40 meters per second. I am sure my base unit of inertia is kilograms. Even if I look at my equation sheet and I go to the back side of it, I can see that it's kilograms. Right? Because I've got this nice little chart of unit symbols, which are my base units for everything. Isn't that helpful? And then I have my unit prefixes under the metric system. And now just solve this. The speed of my ping pong ball. So let's see, mathematically, I'm going to figure out a number for my right side and then divide it and square root it. So I'm going to figure out that number for my right side. 1.45 times 40, and the 40 gets squared. It is, because 145 grams converted to kilograms would be 0.145. Move it over 3 places. And then I would divide that by the inertia of my ping pong ball. And then that's v squared, but I want v. It should end up 293 meters per second. I type it into the space. Oh, you got it? velocity gets squared. Yep. Yay. Yep. Now, if you need help individually, I'll come around and check your work for you. All right, we're going on to number 5 here with our monkey swinging from one branch to another one that is higher. What is its change of potential energy? Key concept to keep in mind here is that potential energy is due to position. So maybe as the position of the monkey changes as the monkey changes, the PE changes. PE graph is due to his weight and height. And you might even put that you expect the PE graph to increase. That might be a good thing to have in there, just to show you understand that if he goes upwards, in other words, further from the center of the Earth, it's going to increase his gravitational potential energy because its position is now further from the Earth. So they want to know how much the potential energy grav changes, and that would be potential energy final minus potential energy initial grav. Where here? Grav, short for gravitational. Yeah, and then PE final grav and PE initial grav. So, let's see. So what I'm picturing over here is we got this tree, we got a branch, and Mr. Monkey goes up here, and this is for me is 1.1 meters. I think that's how far this is. Right? Yeah. So he jumps from the lower branch to the upper branch. So PE grav equals his weight, mg, the final height, minus his weight. Remember, that's the force that we're doing work against, his initial height. So that force that gives us this energy due to our position. And so I'm just going to group some things together here. H final minus H initial, right? Just pulled the mg's out. Yes? No? Maybe? Yeah. And let's see what I know. He's got an inertia of 8 kilograms. They don't say it's a space monkey, so I'm going to assume that we're on the planet Earth. And the change in height is 1.1 meters. So I can just now substitute in for our non-space monkey, 8.0 kilograms. On the planet Earth, the gravitational field strength is 9.80 newtons per kilogram. Change in height is 1.1 meters. And I get my answer. And let's see, let's double check. Kilograms, newtons per kilogram, meters, that's going to leave me with joules. And I'll get some numerical answer. if I pull out my calculator, I do. Yes, that when you put a parenthesis around a number and you put it next to each other, that means multiply. So that's what I'm going to do here. Multiply those all together and get 86.2. Let me know if you need help individually on this. All right, so we're going to go on to number 3 here, where we have a rock. It is thrown straight upwards, and someone does this much work on it, and then they're asking how high does it go. Well, keys to remember here. Let's see. When I do work on the rock, it changes its energy. Now, if you're throwing something, what type of energy does it have just to release it? Anybody? Especially people ask for number 3. When you do work on this rock or throw something, what type of energy does it have just to release it? Kinetic energy, because it's going to be hopefully moving when it leaves your hand, right? What happens is, so the person throws this rock and gives it this velocity up, so it has lots of kinetic energy. Then the rock goes up. What about the very top of its path? Does it have lots of kinetic energy still at the top? No, because it stops, right? That's why it changed direction. So at the top, it's going to have a lot of potential energy gravitationally. Because as it went up, the weight of the rock did work on it and changed its kinetic energy to potential energy. So that would, I would have that in my Y also. As it went up, the weight did work to change the KE to PE grav. So that's the whole reason it slowed down as it went up, because more and more work was done on it by its weight. And that changed it from kinetic energy to gravitational potential energy. Yes? Yes. Yep. Yep. So, work is done on it. That gives it kinetic energy that it had at the bottom. And then work is done on it again, which takes that kinetic energy and changes it to PE grav at the top. So whatever work is done on it is going to eventually be the same as the PE gravitationally it has at the top. And I believe I'm told the amount of work that's done on it, right? Yeah. So I know that. I know my PE gravitational at the top would be the weight of this rock times the height at the top. Now let's substitute in. 80 joules. The mass, 1.45 kilograms. I'm assuming this is taking place on Earth. Per kilogram. And the height. It's always good to have a variable to look for. There you go. Do your math and it will come out. Let me know. know if you need help individually on this one. Alright, so we're going to complete the set by doing number 4 here. We've got a spring, has a spring constant, and remember, a spring constant is a physical description, it's a numerical description of the physical properties of the spring. So, kind of like saying it's blue, but a little more numerically. How much must the spring be stretched to store this much potential energy? So we're changing the position of the spring. We're stretching it, therefore the energy of position, which is potential energy, is changing. So that's what I would put here in my Y in this, in that the position is changing so the potential energy changes the position. The force is not constant. When changing the position. So that's important to note so you don't just make the mistake saying, well, what's the force, what's the distance? You need to take into account that that force is constantly increasing linearly as you stretch it. So, and that's why you end up with that the potential energy elastic or spring, you can write it either way, is 1/2 kx squared. They're asking for potential energy, the change in that potential energy, right? Let's see. They're asking how far it must be stretched to change that, and that's 1/2 k and then delta x quantity squared. So the amount we're going to change it is 27 joules. Nicely, that's already in my base units of joules. 1/2 by k is 44 Newton, 444 Newton meters, which is my base unit again. I'm left with delta x squared, and I'm solving for delta x. So let me know if you need help on that one individually, and I'll be glad to come over and look at your work. What's up? What's up?